All right, so let's continue what we were doing earlier. So we have the following problem. So example 1.3. The rest energy E of an object. So any object has its associated energy, internal energy, or external energy, etc. But this is the rest energy. So if it's sitting, it has an associated energy where it has c squared in the equation, which is the famous Einstein's equation. E is equal to mc squared. So an object with rest mass. M is given by Albert Einstein's famous equation. Famous equation. E is equal to mc squared, where c is the speed of light. Heat of light in a vacuum. Find E. Find the energy. Find the rest energy for electron. Find E for an electron. For which the mass M is 9.11 times 10 to the negative 31 kilogram. It's very small, very tiny mass, very tiny mass. So the SI unit for energy is joules. The SI unit, which is how much we move really, how much we move newtons. So the SI unit for energy is a joule. And 1 joule is 1 kilogram meter per second squared times meter, or 1 kilogram per meter squared over s squared. So we just simply substitute the values, and we have 3 significant figures. And I didn't really explain using orders of magnitude. We can actually understand significant figures better than if we didn't have orders of magnitude, because we can write the significant figures times powers of 10. So this is the orders of magnitude. Like orders of magnitude is like powers of 10. All right. So here, the energy is 9.11 times 10 to the negative 31 kilogram times 2.99792458. So that's the speed of light times 10 to the power of 8 meters per second, and all of that squared, because the equation is E is equal to mc squared, where c is the speed of light. So that evaluates to, after taking three significant figures, we will have, first of all, we'll write all the figures. So all the figures by a calculator: 7, 6, 5, 9, 6, 7, 8 times 10 to the negative 14 kilogram per meter squared divided by second squared. And so the energy is 8.19. Because the 7, we're taking three significant figure, and besides the 8 there is a 7 which is bigger than or equal to 5, so we change the 8 into a 9, times 10 to the negative 14 joules. So that might seem tiny, but that's a very large amount relative to the mass of the electron. So so let's form. So there is a little bit of passage about how we can use orders of magnitude to approximate things. So I'll leave that for you guys. It's just like a little bit of math, and it's not very interesting. So let's head off to vectors addition and vector subtraction. So vectors and vector addition. So vectors has associated magnitude as well as direction. So you draw a vector from the origin. So let's just start with 2 dimensions. So let's start with this vector in blue. This vector in blue has associated beginning as well as an end, and its direction in the plane is given by the head of the arrow. So that's where it's headed. So, as I said, vectors has associated magnitude and direction associated to it. The magnitude is the number it represents, and the direction is how far relative to some origin that we have. So normally we take relative to the east and counterclockwise as positive. So clockwise means negative relative to the east. So this east, west, north and south. So let's start by adding. Let's see how we can add vectors. So if we have 2 vectors, the blue and the pink, so we just place the pink vector. One of the ways that we can do it is place the pink vector associated on the arrow of the blue vector, and we go from the origin up to that vector. So we go from the origin, the output will be in black. We go from the origin to the end of arrow of vector that is in pink. Alright. So that's one way we could do it. Another way we can do it is by completing the parallelogram. So let's see how we can do that, and let's see what I'm even talking about. Yes, alright. So we have a blue vector and a pink vector. So we complete a parallelogram. I'm gonna do it in black. We complete the parallelogram here. And then the output will go from the origin to the end to one of the vertices of this parallelogram. So that would be your output. All right. So that's how you could add vectors. Let's see how we can subtract vectors.